So we finally completed all of the content that we need to know for this unit, but now comes the part where we put it all together and start tackling some pretty complicated problems. So you might recognize this list of steps. This showed up around lecture 6, but I've expanded it. I've added some more information now that we've learned a few extra things. So here are the problem-solving steps we're going to do anytime we solve a problem, and then I'm going to go back and apply it to the example that we started with. First, you're going to draw a free body diagram for your object. There might be multiple diagrams if there are multiple objects. Then you're going to draw a set of axes that line up with the incline of the object. And any vectors that aren't aligned along those axes, you're going to break into components so that all of your vectors are either directly in the x direction or entirely in the y direction. And then you're going to consider each axis in turn. And in the x direction, you're going to add up all the forces that are in the x direction, set that equal to the mass times the acceleration in the x direction. Then you're going to do the same thing for the y, add up all the forces in the y direction. That's going to be equal to ma. And when we say a, we mean the acceleration in the y direction. And again, by x and y, I mean these new diagonal axes that we've drawn. It may not be perfectly horizontal and vertical like you're used to, but we might have tilted them. Then you're going to remember that there's two other equations that you know. If you see Fg in one of your forces of sums of forces, you can replace that with mg. And if you see Ff for the force of friction, you can replace that with mu Fn. And now you've just got a whole bunch of equations, a great big system, and you're going to start solving. So let's apply this to this example that we were working on in the previous videos. So I took a little bit of a detour to show us how to do this trig, but let's backtrack and remember that this question had one more part. Find the friction force impeding the motion of this object. So I've got to add one more force to my free body diagram. There's a force of friction. Of course, friction acts along the surface that's causing the friction, and it's going to be in the opposite direction of the motion. So there's my force of friction on my free body diagram. And I'm ready to go. So I'm going to start in the y direction because that one's a little bit easier. I don't have any acceleration. My acceleration in the y direction is going to be 0. So that's going to make it a little bit easier. So sum of the forces in the y direction. Fn minus Fgy equals ma. And that's going to be, in this case, 0 because there's no acceleration happening in the y direction. I'm going to rewrite this equation, only instead of Fgy, I'm going to replace it with the expression that I found over here. So I'll have Fn minus mg cosine theta equals 0, or another way of saying that, Fn equals mg cosine theta. I just moved the mg cosine theta to the other side. So there's the sum of my forces in the y direction. That was pretty easy. And now I know what Fn is. That's probably going to be helpful later. Now I'm going to do things in the x direction. So sum of the forces in the x direction. Okay. It's going to be a little bit easier if I consider this direction to be positive. I can do that as long as I'm consistent. As long as everything that goes in this direction has a positive sign and everything that goes in that direction has a negative sign. If I wanted to keep things standard, if I decided to keep, usually we think of right to the right as positive and to the left as negative. If I did that, realize Fgx would be negative, but so would this A. This A would have to be negative 0.3. So if I do that, that's fine. It will all work out. But instead, I'm going to make things a little easier on myself, reduce the number of negative signs I have to deal with, and I'm just going to say, to the left is positive. So that means that the sum of the forces in the x direction is Fgx minus, because it's in the opposite direction, the force of friction and that's equal to ma in the x direction. And remember, x is really, this angle here, and so that a is going to be the 0.3 meters per second squared from the problem. So I'm going to do the same thing that I did above. I'm going to rewrite this, but I'm going to start plugging in things that I know. So f g x is going to be mg sine theta, because that's always true. So mg sine theta. And then I'm going to, oops, that should be a minus sign next. Force of friction, instead of just rewriting ff, I'm going to substitute in the equation that I know for the force of friction, which is mu Fn. That's equal to ma. And then one final step is Fn, I actually already know, I found it right up here. It was equal to Fgy, which is mg cosine theta. So now I'm going to just rewrite this, and all I'm doing on this line is I'm replacing Fn with the thing that I already know to be true, cosine theta equals ma. Take a look at this equation for a second. See if you notice anything that makes your life a little simpler. We can cancel out all of these m's. They don't matter. This is the mathematical proof of the concept that I talked about at the start of this lesson. The fact that when we did that pivot lab with the dry ice pucks on the incline, we were kind of surprised to find that the mass of the object didn't matter. It didn't affect the acceleration. And here we are figuring out exactly why that's the case. Here's the algebraic reason, because we have mass in every one of these terms and it cancels out. Let's think about in ordinary English why that is. The left-hand side of this equation is talking about the forces that are acting on the object. So let's pretend that this object is actually the dry ice puck from that pivot lab from a few months ago. Here are all the forces acting on the left. If the mass gets bigger, then these forces get bigger. The force of gravity is going to pull, it's going to have a bigger force, a bigger pull on the object, pulling it towards the ground. Part of the point of the dry ice lab is that there kind of just wasn't friction, so this whole thing would have gone away, right? It was very, very low friction. So the force acting is mainly going to be the force of gravity, and as the mass gets big, the force of gravity gets really big. But at the same time, the bigger the object is, the harder it is to accelerate. The more force you need to apply in order to get the same amount of acceleration. So if I have a really big object, the force acting on it by gravity is bigger, but the acceleration that it's then going to experience because of that force is going to be correspondingly smaller. If I have a really small object that I'm sliding down an incline, the force of gravity is going to be small. mg is going to be relatively small, and gravity will not apply as much of a force to that object. But at the same time, it doesn't need as much of a force. It has less mass, it has less inertia. That smaller force is going to cause a correspondingly larger acceleration on that same object. So that's why we found in that pivot lab that the mass of the object did not affect the acceleration. The mass cancels out. But what is left in the equation, what is still actually going to matter, is the angle. The angle is going to play a role in determining exactly how big that acceleration value is. So, finally, I'm just going to finish this problem off with some algebra. So, you guys know I like to just do everything in algebra and plug in at the end. So that can be kind of tricky. Sometimes we forget what the heck we were doing. This question was asking us to find the coefficient of friction mu. So I'm going to do a little bit of algebra and just solve for mu. So g sine theta minus a, and then I'm going to add this to the other side, is mu g cosine theta. And so if I just want mu, it's going to be equal to g sine theta over, minus a over g cosine theta. And then very last step, I'm going to just plug values in for all of these things. I have 9.8, sine of 32. Remember to put your calculator in degrees. The A was 0.3. over 9.8 cosine 32. And if you do all of this math, you get mu equals 0.59.